So I promised a little bit of help on this week's homework. So let's start by trying to help a little bit on these. So I don't know, maybe I'll do something similar. Let's try to show what the limit of n over n plus 1 as n goes to infinity is. Which of course you know what it should be. From your intuition from Calc 1, you know that that should be 1. Let's actually try to prove it. So how is the proof going to go? Maybe I'll split the page in half. Proof, and here will be the scratch walk. Hopefully I don't regret this. So what do? You let epsilon be bigger than 0. You let big N be something that you get to choose. You let little n be bigger than big N. And then what do you need to show? You need to show that the absolute value of n over n plus 1 minus 1 is less than something. So let's do the scratch walk over here. N over n plus 1 minus 1. Let's simplify that. So you know how to simplify things. Right? Get a common denominator. N minus n plus 1 over n plus 1 equals, well, you stare at this for a second, you see that that's negative 1 over n plus 1. You still have absolute value bars. Absolute value is going to make that negative positive. You'll get 1 over n plus 1. And now you know what I'm about to do. So this was the step which is like simplify. Now that it's maximally simplified, let's use the fact that little n is bigger than big N. So if little n is bigger than big N, then little n plus 1 is 1 over little n plus 1 is less than 1 over big N plus 1, as little n is bigger than big N. And now what do? You set that equal to epsilon, and you solve for big N. So looks like an epsilon of 1 over big N of 1 over epsilon minus 1 will do the job. And right, there's always more than one choice of epsilon you can use, but this is the one that seems to be being handed to me. So let's let big N be 1 over epsilon minus 1. So what is this? Well, it simplifies to n minus parentheses n plus 1 over n, which is equal to absolute value of negative 1, n plus 1 over n plus 1. And if you like, that's just by algebra. Simplifying. Right, I don't want to see you guys doing this shit on your homework, but that's cool. I'm not turning this in. So that simplifies down to no absolute value pairs anymore. Just 1 over n plus 1. As little n is bigger than big N, little n plus 1 is bigger than big N plus 1. So 1 over little n plus 1 is less than 1 over big N plus 1. So n over n plus 1 minus 1, we've simplified down to 1 over n plus 1 is less than 1 over big N plus 1 is equal to epsilon by our choice of big N. Nice. So what have we shown? Concluding sentence. Thus, for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, absolute value of n over n plus 1 minus 1 is less than epsilon. So n over n plus 1 does indeed converge to 1. I shouldn't have a calendar event today. It's Tuesday. No, that makes a lot of sense. Okay. I apologize for the interruption. So hopefully that was helpful. The next one that I'll try to give you a little bit of assistance on is this. So I'm not going to give you the proof. If you like, I'll give you an idea of some scratch walk for 2. And again, I don't care how you spell scratch walk. This is scratch walk. I don't care. So I'm going to list the assumptions. So I know that absolute value of an is less than or equal to 1. I know that bn converges to 0. My goal is an times bn converges to 0. I'll give you the how it should start. Let epsilon be bigger than 0. Next, come up with a choice of big N. And maybe this is the only thing you know. Since bn converges to 0, there exists a big N such that for all little n bigger than big N, absolute value of bn minus 0, which is the same as just bn, is less than a quantity that you get to pick. And let's figure out how to pick that quantity. So I eventually want absolute value of an. So here's the bit that's actually scratch walk. An times bn minus 0. I want that to be small. So it's obviously the same as an times bn. That's the same as an absolute times absolute bn. An, by assumption, is less than or equal to 1. bn, well, I can make that as small as I want. I can make it less than anything I want, so I can put anything I want here. Can you think of something you could put there that would, say, result in this being equal to epsilon? I mean, you can. I'm not going to say it because you already know it. So whatever goes here, you get to put that right here. So maybe here I'll say what's going on here. Here I'm using since absolute value of an is less than or equal to 1 by assumption, and since little n is bigger than big N. Cool. So I think that's all the help I'm going to give you on that homework. I'm going to talk a little bit more now about this homework. So this one I'm having you do a few things. I'm having you show that if A converges to A and Bn minus A converges to C, then it follows that Bn converges to C plus A. And maybe I'll even give you the following hint. You've stayed with me for so long. Bn, that's the thing you want to show converges, is the same thing as Bn minus An plus An. Now use some limit laws. So that means you don't need to show me any epsilons or big N's in this proof. You can appeal to things we've already proven. Let's let an be a sequence and a be a real number. Suppose the absolute value of an converges to a, then absolute value of an converges to absolute value of a. I mean, what do you need to do? You need to study absolute value of absolute an minus absolute a. Look at the lecture on absolute value. There will be a useful result about absolute value. Here's a false proposition. For any sequence an, if absolute value of an converges, then an itself converges. And that's a false proposition, so I want you to find a counterexample. And to do it, well, just start thinking about a sequence which diverges, because you need a sequence for which diverges, which fails to converge, and yet which has the hypothesis true. So we don't know that many divergent sequences. Pick one. Okay, so here's the one that's actually hard, the reciprocal law. So let's let Bn be a sequence which converges to some number b. Suppose also that for all little n in the natural numbers, Bn is not equal to 0, then I claim that the limit of 1 over Bn is the same as 1 over b, which has to be true, right? What else could it be? So here's the idea that I'll give you. So there's kind of a step-by-step guide. So step 1, I want you to show there exists some big N such that for little n bigger than big N, absolute value of Bn is less than absolute b over 2. And I'm even here telling you what epsilon to use for this step. So what am I saying? I'm saying use. There exists some big N1 such that for all little n bigger than big N1, absolute value of Bn minus b is less than absolute b over 2. And then do the same trick that we used in the multiplication rule. That is, absolute Bn is the same as absolute Bn minus b plus b. Something like that, yeah. There's another hint. Look at that. Step 2. Bn is bigger than b, and something that you get to choose anything you want there, is bigger than 0. I mean, you have to pick something that walks, for which this last equality is true. So there exists some big N2 such that for all little n bigger than big N2, absolute value of Bn minus b is less than that thing that you got to pick. Simplify absolute value of 1 over Bn minus 1 over b. Do some algebra. I don't care about the intervening steps. I know you can simplify. Simplify it maximally and then put the result there. Use the fact that little n is bigger than big N1. Since little n is bigger than big N1, you can use this. Since little n is bigger than big N2, you can use this. And whatever the result is had better be equal to epsilon. And that should even give you a choice of what should go in those parentheses. So that's, if you like, the hardest of the homework problems. And I've given you, I think, a pretty good guide to start. So there is actually the limit law for quotients, not just reciprocals. Prove this as a corollary. That is, I don't want to see any epsilons or n's in your proof of this claim. I want you to use the lemma that you just proved, the reciprocal law, as well as the multiplication rule for sequences. Because, well, an over bn, that's the same thing as an times 1 over bn. So if you can explain to me why an converges to a, it's given, and 1 over bn converges to 1 over b by lemma 2.2.8, then you can appeal to limit laws. Nice. Cool. So, again, I apologize for canceling class so much. This should be the last of the cancellations. Awesome. Maybe I'll see you tomorrow, but I rather doubt it. Talk to you later. Chris out. Bye-bye.